Please upload compact calculation from our MCU, ensuring design and low latency control for the clock guidance. For imaging, we selected the ESP32 cam. Its compact form factor is ideal for our secure constraint, while providing necessary visual clarity. Finally, to detect mechanism release, we show the overall BDF tactile switch. This mechanical solution avoids the light interference issue combined with optical sensor, providing a high reliability trigger for our file state.
Okay, next, let's examine the descent control system. Our sanity is divided into two distinct phases: a high-velocity parachute phase for initial stabilization and a low-velocity paraglider phase for precision targeting. We use a hemispherical Nomex ripstop parachute with a descent rate of 15.3 meters per second and a closed-sail 40D ripstop paraglider with a descent rate of 4.83 meters per second. We selected a hemispherical parachute based on our trace study, which showed that this shape provides higher drag than a cross parachute. To reduce instability, we integrate a central weight, ensuring a stable descent at 15.3 meters per second. After finalizing the parachute configuration, we choose Nomex ripstop as the material for its high strength and fire resistance, helping protect the parachute from damage during ejection. Finally, we utilize Kevlar suspension lines specifically for their high modulus properties and zero-stage characteristics, which help absorb the initial deployment shock. For the guided phase, we selected a closed-sail paraglider made of 40D ripstop. The closed-sail design provides higher lift coefficient, allowing a smaller, lighter canopy and significantly better guide ratio. To control the paraglider, we utilize ESI-A, a pistol-style actuator. This mechanism pulls the control line to control direction and descent rate. Pulling one line makes the payload turn, while pulling both lines together slows or speeds up the descent. Our landing strategy employs an active 3 degree of freedom kinematic control model operating at 100 Hz. The system uses A2O loop architectures. Out-loop processes GPS and velocity data to generate heading commands. In the loop, executes high-speed servo commands to adjust roll and pitch. Our Simulink analysis confirmed a 4-phase autonomous flight plan that includes a realistic wind model. In phase 1, the payload flies directly toward the target after separation. In phase 2, it follows a watering pattern to reduce altitude while staying over the target area. In phase 3, aligns the system for the final approach and adjusts for real-time view. In phase 4, the system slows down and releases the instrument at 3 meters, providing a safety margin for the 2 meters mission requirements. This dual-loop control system maintains stable and accurate flight even in changing wind conditions. In conclusion, this dual-loop approach results in a controlled descent from 15.3 meters per second down to a precise 4.8 meters per second point, ensuring both safety and accuracy.
Good morning, I am Hakim Tukinda. I will be presenting the mechanical subsystem. focusing on our structural selection, material threat study, and deployment mechanisms. Our cansat primary load-bearing structure utilizes carbon fiber for its exceptional strength-to-weight ratio. For complex internal geometries, we selected 3D printed ABS due to its superior impact toughness and heat resistance compared to standard PLA. To ensure structural safety, we analyze the natural frequency of both the cansat structure and the rocket. We tune our design to avoid resonance, preventing structural failure during high vibration ascent. For our components design, we perform several thread studies to optimize performance for the release mechanisms. We selected design A, which utilized a servo-driven slide crank arm. Our finite element analysis confirmed that this configuration produces lower state concentrations and requires less internal volumes compared to the design B blocking leg. To protect the integrities of our AMU data, we integrated permanent shielding around both the battery and servo motors to effectively reduce electromagnetic interference. Regarding aerodynamics, we opted for the bunter nose cone to ensure a higher safety margin and paired it with a design A container. For the recovery system, the parachute is secured using a central eye-bolt and pivot load spreading plate, allowing deployment loads to be distributed safely and reliably. The payload released two concepts were evaluated. Design A employs a servo-driven slide crank arm, whereas Design B used a servo-driven brake with a rocking mechanism. Based on the payload release performance comparisons, Design A results in lower structural stress, requires less installation space, and has a lower overall mass. Therefore, Design A was selected for implementation. In Design A, the paraglider is stowed using a spring-assisted cap mechanism, allowing organized and controlled packing. This organized stowage reduces the risk of line entanglement compared to passive designs, so Design A was selected. During release, the spring-assisted cap ejects the payload and actively pulls the paraglider out of the container. This provides more reliable and predictable deployment than passive unfolding. For visual telemetry, our cameras are mounted internally. The distant camera provides a clear upward view of the paraglider's health, while the ground camera is recessed within the payload frame to protect the lens during touchdown. Finally, our mass is managed through a detailed budget, with the current total calculated at 1,000.04 grams. This allows us to meet the mission weight requirements with extreme precision.
Okay, next we move to the communication and data handling subsystem. Before moving into the technical detail, I will briefly the overview. The mission system consists of a TNC 4.1 as the payload processors and XP Pro 900HP for wireless communication and an ANTX 150P antenna. The HB configures in unicast mode with network ID 1059 and transmission telemetry data rate at 1 Hz. Our architecture is powered by the TNC 4.1, selected for its 600 MHz clock speed and repeat boot time. This high-performance MCU is essential for maintaining a stable 100 Hz control loop, while running our extended Kalman filter for accurate sensor fusion. For telemetry, we use the ANTX 150P antenna, selected for its flexible placement options and reliable radiation performance. It is paired with the HB Pro 900HP operating at 900 MHz. It provides long-range communication and remains reliable when the payload drifts due to wind. For the transmission control, the payload begins in the start state, where the system is powered on but telemetry visible. During pre-launch, the system awaits for the CX on command to initiate telemetry. Once active, the ground control station can send ST for time synchronization, call for altitude zeroing. Throughout ascent, apogee, and descent, telemetry is transmitted at 1 Hz. After landing, the CX off command is issued to stop transmission. With the telemetry packet size of 936 bits, the data rate is about 0.936 kbps per second. This gives us enough link margin to keep the signal reliable throughout the flight. We implemented 6 main commands: CX to control telemetry transmission, ST for set time, SYNC and SYNP for simulation control and simulated pressure input, call for reset altitude to 0, and make to activate specific mechanisms such as servo. This structured format ensures clear passing, reliability, and operational flexible during the mission.
Next, moving on to the electrical power subsystem, we will examine our power architecture, component selection, and energy budget analysis. Our power architecture is divided into 2 segments, the payload and the beacon. We utilize the severe configuration, providing a nominal 7.2 voltage main bus. This voltage level is ideal for our standard regulator to efficiently provide a stable 5 voltage and 3.3 voltage jet well for the sensor, servo, and MCU. For safety and monitoring, we have integrated an easily accessible solution for rapid pre-launch activation and an IA to electromagnetic sensor for the real-time telemetry of voltage and current node. For our energy source, we selected the Samsung INR 18650 35E. While slightly heavier than some alternatives, its 3500 mAh capacity and high discharge capability of 13 amp provide a massive buffer for our peak server load during paraglider maneuver. Finally, our calculated total consumption is 7.77 watt-hours, even after applying a conservative 70% efficiency factor and a 10% added margin. We maintain a significant surplus of 9.09 watt-hours. It results in a total estimated runtime of 2.06 hours. We far exceed our mission requirement and ensure the system remains active, even in the event of delayed recovery. Next, moving to the core of our operation, the flight software design. This subsystem acts as the brain of the cansat, making high-frequency tasks and mission-critical logic. Our software utilizes a deterministic autonomous state machine from the launch pad state. The system monitors audio to trigger the ascent phase. The most difficult transition occurs at apogee, where the software dynamically calculates the 80% audio threshold. Upon reaching this mark, the system enters the probability state, triggering the separation servo. We utilize necessary feedback as a hardware confirmation of successful separation before activating our PDR-based character control. To mitigate the risk of misfired power reset, we have implemented a non-volatile recovery plan. The software logs the current mission state 1 through 7 and packet call to the import at every transition. If a reset occurs, the system executes an auto-resume protocol, jumping directly back to the last known state to ensure the zero data loss and mission continuity. To validate our mission logic, we developed a simulation mode. The feature utilizes input diversion, where the MCU stops reading the physical velocity sensor and instead processes simulated pressure packet sent via radio from the ground control station. These are high-pitch approach. While audio is simulated, the system continues to monitor real-time battery voltage and GPS coordinate, allowing us to test mission logic under realistic hardware constraints. Currently, we have finalized our flight diagram and cost sensor integration. Our roadmap is toward the critical design build in March, with a primary focus on refining our telemetry processing and realizing fail-safe logic before the launch in June.
Okay, next, we move to the ground control station, which we develop across 3 domains: hardware infrastructure, link margin analysis, and software interface. Our ground control station utilizes a laptop interface with an XP 900 HP module with a dedicated adapter. To ensure 100% mission uptime, we have disabled OS auto updates and implemented an environmental protection kit, including a sunshade and external cooling fans, allowing for over 3 hours for continuous operations. We have selected the AN032 omnidirectional antenna for its high gain and simplified deployment. To optimize signal integrity, the antenna is mounted on a custom ground plane to enhance the radiation patterns. Based on our link margin calculation, the RF system has enough margin to maintain stable telemetry even at the maximum expected range and during aggressive paragliding motion. Our custom-built ground control station software is designed for high situational awareness and is organized into 3 logical modules. Command and control, the left panel. This module handles serial port configuration, real-time CSV data logging, and command uplink interface. Real-time analytics, the center panel features dynamic telemetry plots to monitor altitude, velocity, and orientation trend during descent. Telemetry feed, the right panel, shows raw data package status, giving the operator a clear view of the payload health. This integrated system allowing the ground team to monitor and control the payload throughout the entire flight.
Good morning, I am cansat. I will present the verifications and validation phase. Our testing strategy follows a rigorous bottom-up approach, starting with unit testing for the individual sensors, progressing to integrated bedrock testing to verify subsystem communications, and concluding with full system integrations To ensure mission survival, we have initiated environmental testing, focusing on vibration resistance and thermal stability to match the launch profile. Our design currently meets 92% of mission requirements with full compliance. The remaining 8% are partially compliant, as they rely on our fidelity simulation results. These final parameters will be fully validated during our upcoming field test campaigns. We have identified no insufficient items, indicating a highly mature design for the PDR stage. Regarding our program schedule, we have optimized our workflow to balance missions milestones with our concurrent military duties. By utilizing a risk-managed schedule, we have successfully completed all core design and software development activities. In fact, several integration tests have been completed ahead of schedule, providing us with a significant time buffer for the verification phase. In summary, we have finalized our structural architecture, validated our 5 algorithm through simulations, and secured necessary mission funding, with our core design verified and a clear roadmap towards PDR. The Space Cadet team is fully prepared and confident in our ability to achieve all missions objectives. This concludes our preliminary design review. Thank you for your time and attention. We now welcome any question or feedback from the judges.
Thank you.
All right, thank you very much. Very good.
Thank you, Judge.
They covered everything well. Good. A lot of good detail.
Thank you.
The only issue is the instrument release sensor.
Instrument release sensor is home run, right?
Well, it's a sensor that's supposed to detect when it's time to release.
Yes.
Well, you had push buttons, which didn't seem right.
Can you say it again?
So, find the page.
Okay.
Page 40.
40. Okay, please wait. Right?
Yeah, so the purpose of this slide was to, for you to identify sensors that be used to know when it was time to release the instrument.
These home run we use to detect the payload release and the instrument release together.
Right, well this detects when it's released.
Uh,
The question is, how do you know when to release?
ก็คือเขามองว่าเอาเนื้อมาทำอะไรก็คือเราไปที่เห็นว่า successfully release the payload ใช่ไหมต่อตัวได้ดีแล้ว
we used to confirm that our release date is
successful
successful.
So how do you know when it's time to release?
We use the our flight software to use the our sensor to trigger our flight software.
Okay, so that is what you need to put in this slide is, what sensors and where the flight software you do the release.
Flight software.